To start out, let me say something about like the really big picture setting of the paper. So I think that there's this confusing way of talking about mathematical physics that's very common. And I think that this confusion is sort of exhibited paradigmatically by talk about surplus structure. I think this sort of confusion is really tempting as soon as you introduce first order talk of mathematical representation into physical theories. And so I think that gauge theories are particularly fraught, and I've written a couple papers trying to argue for this point. The point of this particular paper was meant to be that that talk of surplus structure sort of makes a hash out of quantization. So as often happens with first drafts, this one sort of jumped the gun. And I thought to myself, philosophers almost never talk about quantizing gauge theories. And when they do, it's sort of only in loose terms. And so there aren't any deep-seated commitments about quantizing gauge theories that I need to dispute. There's only these general slogans like quantization requires us to treat gauge equivalent configurations as different representations of the same physical state of affairs, things like this. And so that means I should respond in kind, and I won't have to alienate the reader with technical details of what I actually mean. So it turns out I was wrong. Talk audiences, and more importantly, referees, turned out to be pretty committed to a certain story about quantization, despite, I think, there being no particularly detailed telling of the story in the philosophical literature. So a lot of the present paper is me like telling you about a view that I don't like, but that's the reason why. The aim of the present paper is to try to reconstruct and dispute what seems to me to be the most popular story, sort of as ground clearing for this more philosophical point, which also means that I can't totally suppress the technical details. So sorry in advance about this. Okay, so there's 3 parts to this talk. In the first one, I want to reconstruct my best shot at what you might call the received view in the philosophical literature on the quantization of gauge theories. One part of the goal is to criticize this view, and another part is to identify problems that I think it identifies and sometimes avoids. So I think the usual story has identifiable and relatable motivations. I just don't think that the usual arguments carry you through to a view like the one expressed by the slogans. The second part of the talk gives one example of an alternative story. So I think it's an imperfect alternative, but its imperfections are related to the fact that we lack a non-perturbative formulation of QFT rather than any sort of deep philosophical misunderstandings. The third part of the talk tries to draw some local morals for disagreements in philosophy of physics as like a takeaway. Basically, I'm going to say that the stock objections to the kind of view that I'm offering in the second part don't work. The objections don't work. So by the received view, I mean something like what's expressed in the following sources. This is specifically the philosophical literature. You can find similar things in the physics literature, but I mean to be addressing philosophers. Broadly speaking, this view says that certain theories can't be quantized because they contain distinct mathematical representatives of the same physical state of affairs. I think there are roughly 2 related variants of this story that correspond to 2 different diagnoses of what the problem is. What I'll call the conceptual view says that we somehow know pre-theoretically that certain theories can't be quantized. And the full statement of this view comes from Michael Redhead in the paper here. What I'll call the technical view says that you can certainly try to quantize any theory you want, but the multiple representation problem with gauge theories leads to problems with the quantum theory. And I think that this version is most fully stated by Richard Healy in the book I've cited here. The distinction between these 2 views is mine, and it's really rough. I think most of the people on this slide don't say enough about the issue to classify them in one bucket or the other, but they say things that I think are close enough to be a united view. So let me say something in more detail about what the view says, introduce some terminology for it. So we need some kind of quantization scheme to talk about quantization, and I'm going to use path integrals, but nothing really hangs on this. I just like them. The general recipe is you fix some classical configuration space X, some function S on X, which is the action. And then in terms of this data, you can compute quantum expectation values of classical observables using an integral like the one on the slide. So for the purposes of quantization, a classical theory consists of a configuration space X and a function S on X. For a field theory, X is generally going to be some infinite dimensional supermanifold on S, a supermanifold because we can have anti-commuting coordinates for fermions. And the action S is going to be an integral over space-time of some Lagrangian density involving quadratic terms for each field variable and perturbative modifications at higher orders for interactions. Right, so the usual philosophical story says that this scheme is all well and good for many theories, but it breaks down for others. So obviously, as I'm sure many people know, there's in some sense mathematical difficulties with the expression I've written here. You can't think of this integral as an integral in the measure theoretic sense most of the time. The point of the received view, as I'm calling it, is that even if we set aside these problems, there are certain theories that pose a further issue. So what's that? Well, Redhead says the following. Here's the quote, but I'll give you the background first. So there's there are certain classical field theories, call them gauge theories, that feature a distinguished class of transformations on their configuration spaces, called these gauge transformations. Redhead argues at length that if two configurations are related by a gauge transformation, then they represent the same physical state of affairs. When he turns to the issue of quantizing these theories, he begins by saying that in the path integral approach to general gauge theories, a naive approach would involve integrating over paths which are connected by gauge transformations. To make physical sense of the theory, the obvious move is to, quote, fix the gauge so that each path intersects each gauge orbit in just one point. So I understand him to be saying that if we would like to quantize a gauge theory, there's a naive approach where you would take X to be some space of classical configurations that contains distinct elements related by gauge transformations, but that integrating over this space wouldn't make physical sense. He doesn't say what he means by physical sense, nor what kind of integration, nor why this kind of integration wouldn't make physical sense, nor why fixing the gauge would make physical sense or be the obvious move. But I think this is nevertheless the fullest illustration of one version of the received view, where we somehow know that we know the correct classical configuration space pre-theoretically. There's some sort of conceptual problem with quantizing what he's called the naive classical space of states. So I don't think the story really makes much sense, and so I probably shouldn't pin it on him. There are other people who more clearly endorse what I'm calling the conceptual version of the received view. They just don't go into as much detail as Redhead does here. But here's how I would reconstruct the reasoning. The very short version is we should interpret the classical data so that it produces the correct quantum theory upon quantization. Since we've already fixed a quantization procedure, this is a recipe for interpreting the quantum theory, or the classical theory, sorry. So you plug the classical theory into this quantization machine, you check the empirical predictions, and if they don't match experiment, then you reject that interpretation of the classical theory. So I'm attributing this framing to Redhead and others because whenever they talk about quantizing gauge theories, it's immediately after a discussion of the Aharonov-Bohm effect. So I take it that the Aharonov-Bohm effect is meant to illustrate a general pattern or a general procedure for interpreting classical theories in light of quantum results, right? Because you need some sort of principle to match up the classical theory with whatever quantum thing you're appealing to. So let me introduce a notation to rehearse that story. We're going to think of Yang-Mills theory as the paradigm gauge theory, and we're going to take electromagnetism to be the paradigm Yang-Mills theory. A Yang-Mills theory has an associated Lie algebra G, and in local coordinates, some portion of the classical configuration space is coordinatized by a family of real scalar functions on spacetime, A, G, mu, that assemble into a G-valued one form. That is, any G-valued one form gives you a local configuration of the Yang-Mills field, but distinct G-valued one forms might coordinatize the same point of the local configuration space. Using these coordinates, we have a field strength tensor big F, A mu nu on the lower right here, in terms of some coupling constant little g and the structure constants little f of the Lie algebra. And then the Yang-Mills Lagrangian density is the squared magnitude of this field strength, as on the left. So the action S is given by integrating this over Minkowski space. Sorry. Okay. So how do we interpret this as a classical field theory? Well, the usual story goes like this. There's two phases. We start out by noticing that in the case of an abelian Yang-Mills theory, we get something that looks a lot like classical electromagnetism. We then argue that classical electromagnetism can be interpreted as being about an electromagnetic field analogous to the Yang-Mills field strength, big F. The equation of motion for a Newtonian particle moving in this electromagnetic field is a function only of the field strength. And the equation of motion for the electromagnetic configuration is also only a function of the field strength. So the electromagnetic facts accessible to Newtonian matter are fully encoded by F, and the dynamics of these facts are fully expressed in terms of F. And so we should take our the g-value 1 forms to be coordinatizing the space of closed g-value 2 forms. So the idea is we first cook up this electromagnetism-inspired interpretation, and then we ask, okay, what if instead of Newtonian matter, we try to probe the electromagnetic configuration with quantum matter? Well, the equation of motion for a quantum particle moving in an electromagnetic field can't be written as a function of the field strength. It is, g-value 1 forms can give the same field strength, but different dynamics. So we go to the lab and we check, and we find out that, in fact, we do get different dynamics from 1 forms with the same field strength. And we conclude that the space of field strengths is not an adequate classical configuration space for electromagnetism in the semiclassical case, and therefore in the classical case. So what do we do instead? What do our g-value forms coordinatize if not field strengths? Well, we repeat the logic of the Newtonian first pass. In the first pass, we thought the configuration space should be the space of field strengths because it's impossible in principle for Newtonian particulate matter to distinguish 1 forms with the same field strength. Quantum particulate matter discriminates more finely, but on the second pass, we can take 2 1 forms to coordinatize the same point of configuration space if they're in principle indistinguishable to quantum matter. The alternative interpretation we're supposed to adopt here is usually underspecified, but it at least involves an appeal to gauge transformations. So let me introduce those. For any g-valued function, G, this is the Lie algebra function, G, and for any Lie algebra valued function on spacetime, which in coordinates are would be given by a family of scalar fields C, we have a transformation that acts on g-valued 1 forms as on the left here in this slide. So call this an infinitesimal gauge transformation. We can exponentiate this transformation to give a gauge transformation full stop. And since the action is invariant under all gauge transformations, any 2 potentials related by such a transformation will produce the same dynamics for a quantum particle. So we apply the same reasoning as the classical case to the semiclassical case and conclude that 2 1 forms coordinatize the same point of the classical configuration space if they're related by a gauge transformation. So what I just rehearsed is the argument leading up to the passage that I quoted from Redhead. But this reasoning can't get us to Redhead's conclusion. So I won't try to figure out here why the kind of reasoning that I just walked through makes any sense. People have raised problems for it, but I'm just going to grant that it's okay. I basically like it. But whatever else is the case, this reasoning gives a clear recipe for interpreting classical theories in light of quantization. You quantize them and do an experiment. If we had adopted the conceptual view in the case of the Aharonov-Bohm effect, then we'd have to say that the derivation of the effect that Aharonov and Bohm did doesn't make physical sense because it distinguishes 1 forms that coordinatize the same field strength. It seems to be the only reason that you could have some pre-quantization interest in gauge transformations is by something like an appeal to the Aharonov-Bohm effect. And reproducing this reasoning requires you to treat the results of quantization as an open question, as it were. I mean, you should probably bet that gauge equivalent configurations coordinatize the same point of configuration space by some sort of correspondence type reasoning. But that bet's only going to pay out when you quantize the 2 different theories and look at the results. So I don't think we can somehow know from the armchair that there's a problem with quantizing 1 form of electromagnetism. So there must be some other kind of problem if there is one. The other substantial philosophical discussion of this issue from Richard Healy says that there is a technical problem. In particular, he says that path integral quantization of gauge fields involves a difficulty associated with gauge invariance. The path integrals are functional integrals over the space of potentials A, and since many such potentials are gauge equivalent to one another, this involves massive overcounting. Not surprisingly, the resulting functional integrals diverge. So unfortunately, he doesn't say a whole lot more than this. And as I alluded to above, when I introduced path integrals, QFT, they are already full of divergences. So if there's really a problem here, the special gauge theories, then we need to say something more. In the interest of time, I'm just going to say it and be light on the details. But if you like the details, or if you like some discussion of how this divergence relates to the other divergences that arise, I'm more than happy to share the paper. So here's how we evaluate path integrals perturbatively. We're interested in the kind of oscillatory integral on the top line here. Perturbatively evaluating an integral like this involves 3 steps. In the first step, you do a linear decomposition. In the second, you average. And in the third, you use Feynman diagrams to reduce the average to an expression in fewer terms. So roughly, you start by chopping up the domain of integration into regions so that each region contains exactly one critical point of S, turning our integral into a sum over critical points of some integrals. Then you replace those integrals with the total volume multiplied by the average of the integrand. So you do that by approximating S as a quadratic near each critical point, and that gives us a Gaussian integral. We're very clever and know how to evaluate Gaussian integrals exactly. When we're integrating over a supermanifold, as we do in QFT, there are even coordinates that are the commutative ones. There are odd coordinates that are the skew commutative ones. The total volume in this volume factor is a rational function of a linear invariant of the odd quadratic part and a linear invariant of the even quadratic part. The determinant in particular. So surprise. Right, so if you've only got commuting fields like a Klein-Gordon field, then the numerator of this ratio is 1. If you've only got anti-commuting fields like a Dirac fermion, then the denominator is 1. If you've got a scalar field and a Dirac fermion, maybe interacting via Yukawa coupling, then the ratio will be non-trivial. The average density on the right hand, the furthest right here, is given by averaging the integrand, including whatever's left of S, all of the perturbative stuff, using the Gaussian weight. So in the final step, you use Feynman diagrams to reduce this average to an algebraic combination of propagators, which are averages over just 2 coordinates. And these are in turn given by the inverse of the quadratic part of the action. So the takeaway point here is that these integrals are a nice shorthand for these certain asymptotic series. There are three pieces that are relevant for us. There's the sum over the critical points, or the classical solutions. There's a volume term, and then there's this average expressed in terms of propagators. So the volume term diverges when the even quadratic part of the action is singular, or that is, it's not invertible, or its determinant vanishes. These sorts of equivalent characterizations from linear algebra. The average diverges when the even or the odd quadratic part of the action is singular, because what the Feynman diagrams do for us is they reduce this last term, the average of the perturbations in O, to some algebraic expression in the inverse of the quadratic part. And if the quadratic part can't be inverted, then that doesn't mean anything. So why does this procedure choke on gauge theories? Well, because the quadratic part is not invertible. If we take the classical configuration space to be the space of G-value-1 forms, then we get both kinds of divergences here. I'll take the abelian case as a simple one. The quadratic part of the Yang-Mills action is the operator that acts on A as on the left. That is, it's a second-order differential operator sending A to some vector J. If you let A and J vary, then this is Maxwell's equation, written in terms of the potential instead of F. So the quadratic part of the action is invertible if and only if there's a unique electromagnetic or a unique potential associated with every current. And we know that there's not. If two one-forms A and A prime are gauge equivalent, then one satisfies this equation if and only if the other does. So the quadratic part of the action is not invertible, making the propagator undefined. Moreover, because it's not invertible, its determinant vanishes. So the volume term diverges too. Non-abelian Yang-Mills theory has similar problems. And in fact, we run into this problem for a large class of theories. We run into this problem for any theory that has what Gordon Balotz called spoilers, which are roughly speaking compactly supported infinitesimal symmetries of the equations of motion. since these spoil the determinism or invertibility of the equations of motion. So Balot has pointed out that we can use the concept of spoilers to define an equivalence relation on configurations that often coincides with the gauge equivalence relation. And the problem we just encountered is one reason that you might be interested in spoilers sort of in practice. I also think it's a good guide to which transformations you might want to label with the really badly overloaded word gauge. But I've said today I'm going to use gauge transformation to mean that sort of g-valued scalar function I introduced before, and I'm going to stick to this. So is this a problem with massive overcounting, as Healy puts it? I don't think so. It doesn't seem like it. It seems like counting has to mean the choice of the critical points that we're summing over, the different things the solutions we're counting. And that's not the source of the divergences. Each term in the sum diverges, since the volume factor and the average both diverge. I don't want to lean too heavily on Healy's wording, because that seems sort of unfair, but I do want to emphasize that something like the slogan version of Redhead's fix, for example, is not going to work. Even if you pick one classical solution from every gauge equivalence class and sum over these, the integral will still diverge because the volume factor diverges for every classical solution. So I think overcounting talk is misleading. I think overcounting talk continues to be misleading when you look at the usual tricks that people use to deal with this non-invertibility. So I'm going to briefly review these in the way that philosophers usually talk about them, which is as a sequence of increasingly ad hoc tweaks to the theory that we started with. There's basically two things you can do when you have a problem like this. Excuse me. You can change the classical input data, or you can change the quantization procedure. If you change the classical input data, you can either change the classical configuration space or the action. Philosophers who adopt the conceptual view often say that we know that we should replace the configuration space with the set of gauge equivalence classes, but I've never seen any convincing treatment of that theory. Instead, what people usually do is opt to change the action by appealing to an analogy with the notion of a Lagrange multiplier from the calculus of variations. So you might adopt a Lagrangian like this on the top. If we interpret C as a Lagrange multiplier, then at the level of Euler-Lagrange equations, this Lagrangian gives the Yang-Mills equation along with a constraint on the divergence of A coming from the Lagrange multiplier. If we instead interpret C as some constant, like 1, then at the quantum level, it is going to change the quadratic part of the action to the perfectly innocuous Klein-Gordon equation at the bottom of the slide, up to signs in the metric. And then we can go off and happily compute a bunch of stuff in QED if we want. So does this new theory solve an overcounting problem? I don't think so. We're still integrating over the entire space of g-value 1 forms, so we've not changed the domain of integration. It's true that the new action has fewer critical points because we've gotten this new constraint. And so I guess in that sense, we have changed the counting. And so I'm happy to say that there was an overcounting problem here. But I think that this counting talk is ambiguous and it's not doing a whole lot for us. I think a better question now is like, why should we care about this theory in particular? There's lots of ways of modifying the action to give an invertible quadratic part, and lots of these give an empirically adequate theory. Quantization cares about the difference because when we modified it this way, we got a theory that works out. So we should interpret these as different classical theories, given our ground rules, but there's no obvious way to choose one or the other. And people don't want to. They want to say that even though we've made this modification, different modifications give you the same theory because of gauge. And then, you know, that's about it. So anyway, I think it's not worth worrying too much about this because this isn't a good enough solution. So adding a Lagrange multiplier like this mostly works in abelian Yang-Mills theories, but for non-abelian Yang-Mills theories, this Lagrangian gives a non-unitary theory. So, for example, consider the amplitude for two gluons to scatter to two gluons. In Feynman diagrams, the modified Lagrangian gives these diagrams to the first couple of orders. So in the first one, we've got two gluons that sort of bang into each other and then go off by themselves. And then the second one, we've got two that annihilate into a gluon, which then decays into two gluons, and so on. In terms of Feynman diagrams, so we've got all these diagrams. We've also got some of the permutations that I didn't write down. Conditionalizing on different possible polarizations of the incoming and outgoing gluons, we find that the probabilities for the possible scattering products add up to less than 1. So the chance that something will happen when you scatter 2 gluons is less than 1. That's a failure of unitarity. Feynman was the first person to notice this when he was using Yang-Mills theory as this toy theory to investigate the quantization of Einstein gravity, because it was this thing that, this simple case that only mathematicians cared about in '63. He also noticed that this problem could be solved by introducing what he called an artificial dopey particle, which gives one more diagram at first loop order here, where the dashed lines are the new particle. Adding this diagram and all of its higher order friends fixes the unitarity problem. But now we have a new particle to understand on top of the modifications that we introduced to the action. And this particle is really weird. We can back engineer a Lagrangian that gives us these diagrams, which looks like this. But it's a weird Lagrangian. First of all, the quanta of this new field C can't appear in external states. Second, the C is an anti-commuting scalar field, so it violates the spin statistics relation. And then third, it has the wrong sign on its kinetic term. So it's a ghost in the technical sense of a negative energy mode. No one really worries about these features, and I think they're basically right not to. But they usually cite bad arguments in favor of ignoring them. And I'm going to come back to these in the third part. For now, I just want to point out, we've expanded the action to fix the divergence problem. And then we've expanded the domain of integration to include this new ghost field. And as it turns out, this still isn't good enough. But I'm going to stop going down this path at the moment. I think making all these little piecemeal modifications is a bad way to go, and most philosophers agree. But they usually think the solution is to just change the quantization scheme. The ad hoc fixes that I've been introducing so far can be reproduced by multiplying the original path integral by various clever forms of 1 and then ignoring some of the divergences. This procedure, the modified procedure, is more systematic, but it doesn't always work. For example, sometimes does, sometimes doesn't give you a perturbatively renormalizable theory. It only works for certain kinds of spoilers in Bilot's sense. These tricks sometimes give you a way to throw out some infinities, but I think in the end, they're really not any less ad hoc than just changing the action and configuration space by hand. And I mean, really, I think that changing the quantization procedure is just giving up on the game. It only makes sense to talk about comparing different interpretations of the classical theory in this way if you're holding the quantization scheme fixed. If you're not, then what you're really comparing is a classical theory paired with a choice of quantization scheme. I mean, if you want to do that, good, great. That's probably what you should do if you're doing physics. But if you want to use quantization to interpret the classical theory, as philosophers often want to do, then you need quantization to mean the same thing from case to case. And so really, I think that that sort of direction is not useful. Okay, good. So that's the negative part. For the positive part, I just want to describe an alternative story about quantization of gauge theories and then say why it's a counterexample to some of the claims that philosophers often make about ghosts. For my broader philosophical purposes that I alluded to at the beginning, all I really need is for this alternative to be coherent. And like I said, I think it's got some problems, but I want to tell you about the cool parts. And then I'll say why it doesn't lead us into trouble when it comes to ghosts, despite what people like Weingard have said. So, in the first part, I argued that the conceptual version of the received view doesn't really make any sense, and that while the technical version was right in identifying a problem, it doesn't give us an adequate solution. If we want to hold our quantization procedure fixed, we simply have to conclude that one-form Yang-Mills theory can't be perturbatively quantized. Really, this is just the same situation that we found in the case of the Harnaff-Bohm effect. Two-form electromagnetism just doesn't give us the dynamics for the quantum particle, and one-form electromagnetism does. So anyway, this means that we need to modify either the action or the classical configuration space. We've already seen that there's too many ways to modify the action, and that attempts to do so lead you to modifying the configuration space anyway. So let's try to start with modifications to the configuration space. I mean, in the end, all we can really do is just try everything we can think of and see what works. But I think that there's one obvious thing that we haven't tried yet. What puts the two versions of the received view in the same box is that they both think the problems with one-form Yang-Mills theory should be blamed on multiple representation. that is the fact that gauge equivalent one forms represent the same physical state of affairs. The conceptual and the technical versions of this view just locate the specifics of the problem in different places. Like I said at the start, this makes me uncomfortable. I don't think there's anything strictly wrong with talking about representation in contexts like this. I just think it's never necessary and it can often be dangerous. I think talk about representation here is a lot like talk about truth. I can say things like, it's true that there are 6 quarks, but if this is just going to be a freestanding assertion, I should just say there are 6 kinds of quarks, or at least I might as well. And if I go around all the time saying things like, it's true that P, then there's a danger I'm going to start thinking that there's something called truth that's a property of propositions in some substantial metaphysical sense, and then I'm going to need some story about it, etc. I think representation talk poses similar dangers when it comes to mathematics in particular. I think there are other cases where representation might need a more substantial story. Anyway, take Yang-Mills theory. What could it mean to say that gauge equivalent one forms represent the same physical state of affairs? If this claim has to have any bearing on our problem, then it has to be a claim about the classical configuration space or a claim about the action. Gauge transformations are certainly related to the action, right? They're spoilers for it in Bloch's sense, but they'd be spoilers even if they were just proper physical symmetries too. It's hard to see what kind of change to the action could correspond to taking on this new commitment about the significance of gauge transformations. Certainly adding a Lagrange multiplier to the action doesn't do it. That's distinguishing gauge equivalent one forms, which is the opposite of representing them as the same. So can we change the configuration space? I think this is what representation talk in this context is usually after. I think that the claim gauge equivalent one forms represent the same physical state of affairs is really a denial that the space of G-valued one forms is the configuration space of the theory, combined with an assertion that the map from the space of G-valued one forms to the configuration space sends gauge equivalent one forms to the same configuration. Okay, but then what is the configuration space? Lots of spaces admit a map that identifies gauge equivalent one forms. For example, the space of field strengths admits such a map. In light of the Aharonov-Bohm effect, we shouldn't be tempted by that space, but what space should we use? The claim that gauge equivalent one forms represent the same physical state of affairs is just silent on the issue. I mean, I think this is one useful thing that representation talk does for us. It allows us to do things like this. But it doesn't answer the question. So one natural option is to try a space that's as close as possible to the space of G-valued one forms while still admitting the appropriate non-injective map. This suggestion requires us to choose a definition of a space that's as close as possible. And different choices are going to give different results. For example, if by space you just mean set, then the result's going to be a set of gauge equivalence classes of G-valued one forms. I think this is a pretty implausible option. Whatever else we know that our configuration space has to support Taylor expansion of our action in order to define the perturbative integral. And so whatever we mean by space has to support differentiation, and sets don't. Anyway, at this point, I think our choices are about as constrained as they can be, and there's nothing we can really do except try something. So here's something that I like. It's the smooth groupoid picked out by the requirement that it be as close as possible to the space of G-valued one forms while making gauge transformations into identities, that condition that we adopted. This is the category in which an object is a G-valued one form and an arrow is a gauge transformation. It has a natural smooth structure coming from the smoothness of the data that makes it up. And in particular, it supports the kind of Gaussian approximation required to define the perturbative path integral once we differentiate or look at the tangent, something like the infinitesimal neighborhoods. So here's a more concrete description of this. The infinitesimal neighborhood of some point in configuration space looks like the supermanifold coordinatized by a pair AC, where A are even coordinates that assemble into a G-valued one form, and C are odd coordinates that assemble into a G-valued scalar function. The even coordinates coordinatize the objects of the groupoid, while the odd coordinates coordinatize the infinitesimal gauge transformations. The situation is analogous to the tangent bundle on a plain old smooth manifold. The first set of coordinates picks out the point in the manifold, which is, in our case, a configuration. And the second set picks out a vector at that point, or in our case, an infinitesimal isomorphism. In these coordinates, the infinitesimal isomorphism structure is encoded by a differential operator delta that acts on the coordinates as shown on the slide here. It's basically the change induced by an infinitesimal gauge transformation. Any function of the coordinates A and C that's annihilated by delta gives you a function on configuration space. The Yang-Mills Lagrangian is one example. Two functions of the coordinates give the same function on configuration space. So two different expressions in terms of A and C are the same function on configuration space if their difference is of the form delta h for some function of the coordinates h. In particular, L and L plus delta h are two coordinate expressions of the same function on configuration space for any h. So the function on coordinate configuration space given by the Yang-Mills action has lots of coordinate expressions, as does any observable. What do we get when we quantize this classical theory? Well, the first thing to notice is that the usual coordinate expression for the Yang-Mills action only depends on A and not C. And that means that the odd coordinates in the odd coordinates, its quadratic part vanishes. The volume term of the perturbative expansion of the integral is therefore a 0 over 0 indeterminacy. And that's great. This is wonderful. Indeterminacies mean that we chose our coordinates poorly, and we can cure them by changing our coordinates. And it suggests that the divergence in the propagator is just a coordinate singularity. The propagator is not a function on configuration space anyway. So all we need is another presentation of the Yang-Mills Lagrangian, one that explicitly depends on the odd coordinates and is invertible on the even coordinates. And these are a dime a dozen. So we definitely have a well-defined quantum theory. It really is just one. The Yang-Mills action uniquely specifies a function on configuration space, and different presentations of this function lead to the same quantum theory because they're different presentations of the same function. The quantum theory produced by this classical theory is basically just Feynman's theory with the ghosts and all. The ghost particle is to the odd coordinate C, as the photon or gluon is to the even coordinate A. For my part, this resolves the worries about the weird formal properties of ghosts. If they were quanta of some matter field, that would be really weird. I mean, they would have weird properties, but they're not. They're quanta of the isomorphism structure, I suppose. So you might think that's a weird thing to be, but it seems to me that the main reason that you might think it's weird would be if you thought Feynman diagrams were depictions of little guys running around and banging into each other, which is how I was talking earlier. I don't think you should interpret Feynman diagrams this way, and neither do most people in the literature, so I'm not particularly bothered by this. Anyway, I think that this classical theory has a lot of virtues. In addition to the motivations I stepped through a moment ago, I think it dispels a lot of the mystery that gets ginned up by talk about circle structure here. But mostly, I just think the standard story has a lot of problems that this one does not. So to finish off, I want to address the main worry that this story I'm offering generates. So every philosophical discussion that touches on ghosts dismisses their importance by appealing to some arguments from Robert Weingard in 1988, some arguments that ghosts are mere notation. If Weingard's arguments worked, then I think they would pose a problem for this groupoidal configuration space, since ghosts are decidedly not mere notation in this theory. They're quanta coordinates on the gauge structure. But his argument doesn't work. So he gives two arguments, one specific and one more general. I'm going to call them the convention dependence argument and the electromagnetic analogy argument. The convention dependence argument, he appeals to the same gluon scattering process that I talked about earlier. The convention dependence, his argument points out that for certain calculations, we can choose a presentation of the action that lets us ignore diagrams that contain ghosts. So when we're reducing the Gaussian average in the last step using Feynman diagrams to this algebraic combination of propagators, we can choose an H such that L plus delta H assigns 0 to this last diagram and to any other diagram that includes ghosts. So ghosts don't directly appear when we write out the Gaussian average. Their presence is only felt sort of indirectly through the fact that the gluon propagator is not singular and that the overall volume converges. What we really care about is the entire perturbative expansion, and we can arrange things such that we can compute this expansion without needing to talk about ghosts. And so we should think that ghosts are mere notation, is how his argument goes. So I think that argument's fine as far as it goes, but it doesn't get all the way to the conclusion. What it tells us is that we should be careful about moving too quickly from Feynman diagrams to interpretive conclusions. Weingard showed us that in a particular case, we could ignore ghosts, at least after we set up our collection of Feynman rules. But what we really need to establish, the claim that he makes, is an argument that we never need to talk about ghosts at all, and that isn't true. So Weingard recognizes the need for this more general argument, and he appeals again to the Aharonov-Bohm effect to make it. He points out that when you're doing semiclassical electromagnetism, you can't always assume that the potential one form is 0, even when the field strength is 0. So he says this is evidence that the one form is really part of the equation, or it's not mere notation in the Aharonov-Bohm case. So I suppose more generally, the idea is that some mathematical gadget is more than mere notation, just in case you can't transform it away using some set of salient transformations. So Weingard gives a mathematical articulation of what he means, and I'm just saying transformed away here for simplicity, but it's the same mathematical thing in both cases. The general claim that he makes is that the convention dependence argument is an instance of a much more general fact, which is that unlike the electromagnetic one form, ghosts can be set to zero by applying changes of conventions. I think this just is false. It's not the case that you can always use a transformation to set the ghost fields to zero. Here's a function that prevents you from doing so. I'm sorry to give you this horrific expression at the end of this long talk. There are two important things for us. Right in the middle there, there's a CA, and also there's no H such that this expression is equal to delta H. The fact that it depends on the ghost coordinate in the middle means that if we could always set the value of the ghost field to zero, then this function would also we could always take this function to be zero by changing our delta H convention. But you can't do that. If you could always set, if you could always set the value of the ghost field to zero, then this function would also have to be zero, and it's not. And it's important that it's not because it has empirical consequences. One of them is that the charge of the proton is exactly opposite the charge of the electron, not like within experimental error, but it has to be on the nose exactly the same number. The argument for that is pretty involved, and I think it deserves a lot of attention, as I've said in some papers, but put that aside for now. I think what we should learn from Weingard's first argument is that, yeah, we should try to understand Feynman diagrams in terms of the perturbative expansion, what generates the perturbative expansion behind them. And therefore, when we're interpreting ghosts, we ought to interpret them in terms of the classical configuration space and action we started with. I just think that applying Weingard's general criterion tells in favor of something like the groupoidal configuration space because there are non-trivial functions of the ghost coordinates, and these have empirical consequences. Great. So the goal of this talk was to tell a story about quantized and gauge theories that I think is better than the usual one. On the story I'm offering, quantum gauge theories are built like most other quantum field theories are. Classical theories aren't just the raw materials for quantum theories, but it's generally assumed that classical theories ought to be interpreted so that they give the correct quantum theory upon quantization. This is why the Aharonov-Bohm effect is taken to be evidence against the field strength interpretations of Maxwell electromagnetism. The usual story inverts this reasoning, insists that the quantum Yang-Mills theory should be interpreted such that it's obtained by quantizing the Yang-Mills action on the space of G-value one forms, or the equivalence classes thereof. And this leads to trouble because that classical theory has a degenerate action and therefore no perturbative quantization. So the usual story tries to get around this problem with a sequence of ad hoc modifications to the quantization process, and it takes ghosts to be one of these, or one feature of these modifications. But the modifications aren't adequate in general, and they don't match the gloss that they're usually given. There are other options, like this groupoidal one that I'm talking about, or algebroidal, because it's, local. Some of these alternatives have gauge structure, by which I mean odd dimensions related to the even dimensions that implement the informal idea that configurations related by a gauge transformation are the same. Ghost fields are coordinates on this gauge structure. This alternative story avoids Weingard's complaints, which are usually cited against taking ghosts seriously. If ghosts were just an ad hoc fix to unitarity problems, then Weingard's convention independence argument, I think, would have some bite. But at least on the groupoidal interpretation, they're not. Really, I think they have to be more than just a fix for unitarity problems on any adequate interpretation, as Weingard's general argument actually shows. So I guess the philosophical takeaway is that we should be more careful about what it means to say that gauge equivalent one forms are the same, or that they represent the same physical state of affairs, something like this. Given the things on the table, we should prefer the groupoidal interpretation to the one form interpretation, since the first gives us a good quantum theory and the one form interpretation doesn't. But by the same reasoning, we should prefer the groupoidal interpretation over an interpretation in terms of gauge equivalence classes, since that also has no perturbative quantization. At the level of mathematics, there's not really any ambiguity here. the groupoidal configuration space and the collection of gauge equivalence classes have the same objects, but disagree about the arrows between them. But there's more to a category than its objects. So two categories can agree about their objects without agreeing on everything. I think, you know, people who have talked about the use of categories in this sort of representational capacity have often been hip to the role, to the distinction between the two theories. But for the most part, I think debates over the interpretation of quantum gauge theories have restricted themselves to classical theories that don't have gauge structure. And I think that that's a problem. So that's all. Thanks.